LISA will bring certainly a lot of information, new knowledge. I think especially if you have the coalescence of these very supermassive black holes which are at the center of the galaxies. If they see how they coalesce in the very early phase of the universe, probably this will also give us information, for instance, how galaxies evolved. My name is Philippe Jetzer, professor for physics, and my main activity, research activity, is in general relativity, especially in gravitational waves. Ciao Elisabetta.
Benvenuto, tutto bene?
Sì, e tu?
Sì.
Gravitational waves arise when you have a deformation in space and time. You can imagine them a bit like if you throw a stone in a pond, and then you see also on the surface these waves coming out. The LISA mission is essentially a detector for gravitational waves in space. Today we have some on Earth's ground, where they have already found some gravitational waves, but in space this has not yet done, and it's very important because with the LISA mission we will be able to see gravitational waves at other frequencies from the ones which are on Earth. And thanks to them, we will be able to see other physical phenomena or astrophysical phenomena. And the way we do it is the following. We have 3 satellites, and in each of these satellites, to simplify, there is a cube. These are our reference points. And then between these reference points, you will have laser beams going forth and back. And when a gravitational wave comes, then the distance between these 2 cubes changes slightly, and this difference can be measured. The point is that we would like to measure the gravitational wave coming from objects from which we know that the frequency of the emitted wave is very tiny, and therefore also the wavelength is very big. And therefore you need that the distance between the cube is huge, of the order of some million kilometers. In other words, the Earth is too small to carry out this experiment. Today we are at Thales Alenia. They are building part of the electronics, the so-called front-end electronics for the LISA mission. Why Thales Alenia? Because they have already built the corresponding instrumentation, the corresponding electronics for the so-called LISA Pathfinder mission. It was a mission to test part of the technology which is needed for LISA. My interest for gravitational wave is already old, in the sense that I was always interested for a different aspect of general relativity. And then around 2003, with a colleague from ETH, Domenico Giardini, we somehow come together, and there was the opportunity for Switzerland to enter into this LISA Pathfinder mission, and therefore also in LISA mission. I'm also in the LISA board as a representative of Switzerland, and I'm also in the science study team of LISA from ESA. There we also formulate the science requirement documents, essentially a document which says what LISA should be able to measure, to see. And of course, this information is very important for the engineers, because then based on that they have the qualification, they will know how to build it, how long this instrument should be able to last, etc. LISA will bring certainly a lot of information, new knowledge. Probably there are 3 main points. First, I would say, is to test the general relativity. In other words, if you would see some deviation from general relativity, this would be a big sensation. The second one, if we could see the gravitational wave from the Big Bang. This way we could somehow understand the Big Bang much better and somehow go much closer to the origin of the Big Bang, if I can speak this way. And the third, I would say, is the non-foreseen discovery.